is electric fields. Let's do one example. So let's take a look here at this piece here. We have two charges. We have a Q1, which is positive, and Q2, which is a negative, and between them is 4 meters. Then we have a point charge A on the right. It's a point charge, and between Q2 and A, it is 2 meters. Remember, a point charge is always a small positive, unless they say it's like an electron or something. It can happen that they do that. But if they say nothing, we will make it a small positive charge, which is really important for determining our direction and such. So the question, what I want to do is, this is a positive 8, so I just want to put in here positive, negative, and now it's basically grade 8 work, or the 9 work, when it comes to repulsion and attraction. So the question is, what is the magnitude and direction of the electrical field at this point charge of A? Now remember, electrical fields, if we just look at this charge 2 here, the fields around the strength of the electric field decreases as you increase from distance from it. So use that, so that is how you logically explain it. But on this A, you have Q2 affecting it with its electric field and Q1 also. So we actually have to work out the relationship between A and Q2 and also Q1 and A, but not between these two. We don't care. We just individually work out that electrical field value and that one, and then we get like a net E net value at the end where we just add up the two values. So let's take a look. Let's look at E1. Oh, we shouldn't do that because we can lose marks, but E is equal to K Q1 over R squared. Now remember, we don't care about negatives in these things at the moment, but before we carry on, let's just use the direction as positive. We're going to say right is positive. Okay. But we're not going to indicate direction within this equation. We form our direction based on what happens to this point charge A. Does it get repelled or does it get attracted? And remember, A is our focus. So let's take a look. What is the charge the electric field strength at point A with regard to Q2? We'll do something like this. There we go. So the electric field strength of Q2 at a point charge A, which is some distance away from it. So some distance away from Q2 at that point A, that's the distance, and K is 9 times 10 to the negative 9, and Q, why did I say Q1 there? It should just be that, and we know it's Q2, so let's take a look. E is equal to 9 times 10 to the negative 9, and the charge of that Q2 is negative 2. It is microcoulombs, so it will be, to pause there, I couldn't remember. So yeah, you see that negative? We don't care about it. We just leave it as an absolute or just a positive value because we indicate direction at the end. That's the difference between these questions and the rest. And what is the distance between the two? And it has to be in meters, so just watch out. We are dealing with meters, so we can just put in 2, and remember that squared, because that's terrible. If you get that wrong, you lose 2 marks automatically every time you do that. So we put that in, and we get an answer of 4,500 newtons. Yeah, so what I did, my mistake here, that should be negative 9, that's a positive 9. So we get 4,500 newtons, and let's just look at the directions. Q2 affecting at A, and at A is a small positive charge. Well, A, if everything else is fixed, that Q1 and Q2 doesn't move, or doesn't get affected, we're looking at A as our focus, but how will it be affected by Q2? Will it be attracted towards it, or will it be repelled? And we know a positive and a negative charge, they will attract, so that A will go to the left. All right, so right your left. All right, and for Q1, we set this up. Right, looking at Q1, we have a positive 8 microcoulombs over there, and we're only going to compare this to at A. These two are irrelevant how they interact with each other. We're looking only at A. So how does Q1 affect A with its electric field? So let's take a look. So we have E, the electric field, is equal to 9 times 10 to the 9 multiplied by the charge of Q1, which is 8 times 10 to the negative 6. Remember, we don't care about the plus or minus there. And that's all over r squared. And the distance between Q1 and A, isn't it 4 plus 2? It is 6 meters to A. So we 6 squared. And then we get 2,000 newtons. But now we have to just indicate direction. Q1 is a positive charge, A is a positive charge. So A, if everything else is fixed, A will be repelled because like charges repel, and it will be moving to the right, or want to move to the right. So I'll be right. Right? Yes. Now, so we have the field strength of the effect of the electric field strength of Q2 on that point A, and we have the strength of Q1 on that point A. But let's add these two together. So we say the E net is equal to E Q1 plus E Q2, and here we're going to use that directions. We said right is positive. Let's just maybe repeat that. We have E for Q1, which is 2,000, be positive because it's to the right, and the Q2 value will be 4,500 to the left, so it'll be 4,500, and that'll be negative value, and then we get negative 2,500 newtons, so that'll be 2,500 newtons to the left. All right, straightforward, but if you get the concept, it should be easy. Now the second question is, they can ask if a charge placed at A, let me write this down. There we go. A charge replaces A. It experiences a force of 4 times 10 to the negative 3 newtons to the right. What is the magnitude and polarity of said charge? So we're going to replace A with something, and it will experience a certain force. So let's take a look. We have two equations that deal with force in electrostatics. We have this first one, F is equal to, so we have F is equal to K, Q1, Q2 over R squared, and the other one we got is the electric field strength is equal to F over the charge. Now we cannot use the first one because there are 3 charges in total in the system. And, I don't want to play that one. I think we can. No, it's too much effort. So let's take a look at this one here. So we have this E equals F over Q, but remember it is sort of like the electric field strength of a certain charge is equal to the force between them over the other charge's magnitude. But what we can also do here, in this case, is very important. We can say that the E net, the electrical field strength, the total electrical field strength at a point, is equal to the total force experienced at that point over the charge of that point. All right, so we're going to be using this. Now, what is the total electrical field strength at point A? We said it was, from this Q1 and Q2, it was, we said over here, 2,500 newtons to the left. Well, let's go right positive. So we negative 2,500. And the force experienced between them, that's given. Right, so I actually forgot what I was doing here. So we have this, we said right is positive, so our E net will be 2,500 to the left, and our F net is to the right, and our Q is at the denominator, so I just shift it across, use some algebra. So Q is equal to this value divided by that value, and we get a negative 1,6 times 10 to the negative 6 coulombs, which makes sense because it's being pushed to the right. So if we look at this diagram here, we can replace this A with that point, that charge of, we just want to call it Q3. let's call it Q3. If this is if Q2 will have the gradient effect because it's closer, yeah. If you look at the R squared and stuff, you can actually work it out, but this is the thing that will actually affect Q3 the most. So if this was a positive, it'd actually be moving, the force would be to the left, but the force is to the right. Just got to double check your answer. So there has to be a repulsion, that must be a negative value. You sort of check it like that. So it's not always the case that the charge closest has the greatest effect, but you can look at it that way. All right, so there we go. Here's our example. Oh, like and subscribe and all that, and buy me a coffee.